We started here with the beta core instruments, and we developed a lot of our antibodies around the beta core, both for domoic, okadaic acid, and we tried to make sure our antibodies matched the cross-reactivity profile of different toxins. And the same for the paralytic shellfish poisons. We then looked at multiplexing on the beta core, and this was really our first experiences of multiplexing. And this was successful through a project called MidTal, and we were able to multiplex different marine toxins onto this beta core instrument. And you can see in different regions of France, Italy, Sweden, Spain, Ireland, Norway, Scotland, paralytic shellfish poisons, okadaic acid and domoic acid are in the water column and are of concern. And we published a number of papers around the frequency and the method itself and the occurrence of these particular toxins in the water. The feedback, good method, too expensive, not portable technology. Basically, industry wants something they can use in the field. So, bio to nanosensors. Why nanosensors? Well, they're smaller, faster, require less power to run. We've heard about power supply earlier. Greater sensitivity. They offer better specificity. They're more cost effective. They offer the potential for remote use, and they're simple to use. Why? Because in the laboratory, we're no longer competing with ELISAs and lateral flow tests. We're now competing with the high-end mass specs that really can do multiplex analysis and analyse nearly 300 contaminants in a single sample. Even for marine toxins, they can actually analyse now families of toxins. So we'll move to this portable reader system from Biodiagnostics, and we're working very closely with them using our reagents to build multiplex assays. And what you really need is the reader, the laptop computer, and again, this can be put onto an iPhone for the data analysis side. The fluidics cartridge, which is here, an imaging system in the reader, and the digital, and it's quantitative. It offers rapid detection. It offers also minimal sample preparation. It's field deployable, highly sensitive, highly selective, and you can analyse up to 30 cartridges in a parallel run. And the instrument is only used for the final read step. A single operator can run over 100 tests per day. So the MBio system has a camera, and I showed you the cartridge. All the know-how is in the cartridge. So basically, you have a laser, and the laser will basically shine the beam. The beam will create an effervescent wave, a planar waveguide, and the camera will pick up the signal that's generated here with fluorescent detection on immobilized protein-antibody interactions. So the know-how is in this cartridge. So we're looking for low cost, simplicity in use. So really, we want everything hidden in here, almost like a black box to the end user, that they only have to know how to read their data at the end. So we can immobilize our different combinations of either antibody or antigen for antibody-antigen interactions, and different approaches and how this can be designed. It can also be designed at the molecular level for DNA, RNA, or algal speciation testing. It can be designed then at the residual level for low molecular weight and toxins and contaminations. And it works in the same type of principle as competitive inhibition. So what we tend to do is we immobilize our toxins onto the cartridge. The sample and antibody are mixed and added to the cartridge. There's an incubation with a secondary labelled antibody, and light's directed to the bottom of the cartridge to allow the excitation of the fluorophores and the labelled antibody. The sensitive detection of binding events on the cartridge is observed, and when toxin is present in the sample, there's reduced antibody binding to the surface. So when you have no toxin, and then when you have toxin in your sample, in this particular case, just to show the difference. So simplicity in use for multi-toxin analysis. A method can only be field deployable if your sample preparation is field deployable. So for the lab protocol, we basically centrifuged our cultures or water sample, resuspended, beat for 10 minutes with glass beads, centrifuged and filtered. Yes, that was a nice lab protocol. but sometimes it's very difficult to get a centrifuge out into the field. We also look for non-lab protocols where we take our culture, and what we had was a clever bag, and within the bag was a filter membrane. So the cells are rinsed into, basically the culture's filtered, the cells are rinsed into a vial, and a roller, like your paint roller, is used to crush the sample in the bag to lyse the cells and release the toxin. And the sample is then filtered again through a 0.45 filter. And that is a method that can be used out in the field. Then you add your sample to your assay buffer with your primary antibody. You transfer that to the cartridge. You then add a secondary antibody to the cartridge, and then you read. Depending on the complexity required, it can be a quantitative yes-no, or a qualitative yes-no, or a quantitative provide a concentration. And our initial work looked at single analysis detection for saxitoxin in one hand, and for microcystins then on the other hand. But then we wanted to look at multiplexing. So on the multiplexing, we arranged the array as above. So these were controls, and then we put our microcystin spots, our saxitoxin spots, domoic acid, oxidaic acid, and cylinder spermopsin. And these are the different concentrations of protein that were optimized for the array. Initially, we had a 45-minute protocol based on the manufacturer at the time. They had done some work for HIV testing in Africa, and really their protocol was based around 45-minute. A two-step assay, pre-incubation with buffer, 10 minutes, 15 minutes primary antibody, cartridges washed, another 10 minutes with your secondary antibody, and then washed again and record the data. We've got that down to 15 minutes in a two-step assay with a 7.5 minute primary antibody and sample, and then a 7.5 minute dye labelled and record the data. So really we've got it down to a 15-minute test for marine toxins and multiplexing marine toxins. For antibiotic residues in milk, we have it now working as a 5-minute assay, just with the primary antibody and no secondary antibody required, although the primary antibody is labelled with a fluorescent label. So for single versus multiple analysis based on the 45-minute assay, you can see that there wasn't so much difference in reducing from the sensitivity didn't really change so much other than for domoic acid when we looked at it in multiple or single assay format. When we reduced the time from 45 to 15 minutes, the sensitivity changed a little bit for oxidaic acid in terms of it was actually a bit of reduced sensitivity, and the same for cylinder spermopsin. When we looked at matrix effects and we looked at seawater in terms of the salt content and salinity content for matrix effects, and there was little to no matrix effects for the 5 different assays. The sensitivity that we achieved with the IC50s and the low nanogram per mil are heading towards picogram per mil for the marine toxins, and the same then for the freshwater toxins as well. We looked at a comparison with analytical methods for cultures, and really with the cultures we had a good comparison between PSB toxin presence and toxin absence. And then we looked at 33 different samples from different regions around Europe as part of the MidTal project, and again good correlation of toxin present to toxin absence. The MBio technology was significantly more sensitive than the analytical techniques, the LCMS and the HPLC. So what we got was correlation where we had no false negatives, although we're getting additional work done to concentrate the samples to put them back onto the mass spec to look for the positives, because we were getting some samples with the MBio technology that was positive, but the mass spec couldn't reach those levels of detection. So in terms of the multiplex assays, we developed the antibody array device really as an alternative to the mouse bioassay, because the mouse bioassay for water quality monitoring isn't really sensitive enough, and it was really to look for something that could be sensitive out in the field, because mass spec can't go there. And it was progressed towards the development of electronic mouse, to look for inexpensive procedures to reduce and replace the mouse bioassay, initially for shellfish toxin analysis, but also for water quality monitoring as a prevention tool. So really, we'd like to use the device to look for and monitor algal blooms. We'd like to use it as an early warning tool in fishing and aquaculture, and also for aquaculture harvesting sites for shellfish as well. But also, the device can be built in to redeploy or for an early warning deployment vehicle that can be put out for remote sensing. Just some acknowledgements to colleagues back at Queen's, Sarah, Chris, and to also Mike Lockhead from MBio, and then the partners of the European projects, both MidTal and MicroAqua, and European Union for funding. Thank you.